Hey guys.
Hey guys, how we doing?
Well, we're on to chapter two,
Two. Yep,
and this is kind of an interesting chapter.
it is.
More so in the fact that I would feel like it's not necessarily going to be a bunch of math, but
Right.
more of basically how we conduct business in geometry, a style of thinking.
Yeah. Overall concepts. Yeah.
Yeah. A way we want you to look at geometry as far as when you're looking at these things, you should be thinking, you know, uh, if this happens, then this happens. Kind of like a science class.
Right.
I mean, so
We're getting to the logic of
yeah,
geometry here with
yeah.
this.
So, some of it may seem kind of weird to you guys at first, when you first start looking at some of these ideas, and there's a lot of vocabulary in this chapter, but just stay with it. And remember, this is more of a philosophy of geometry more than anything else.
Right.
So it has to start out with patterns. And one of the things in geometry, guys, that I keep telling you guys that you got to be able to make sense out of the visuals that are given to you. If you don't see visuals, you need to make visuals. But visual patterns in geometry are going to be really, really important. And visual patterns are patterns that have to be seen.
Right.
So I mean, when you look at something like this, okay, maybe there it is. Whoops. So let's go back. So it starts off going, the arrow goes to the right, then it goes up. Then it goes to the left, and I'm sure most of you guys are already thinking, oh, hey, I know where it's going to go next. It's going to go down. And then from here, it should go back to the right. And then from there, so you guys kind of have, this is kind of a basic idea, but you have an idea of what visual patterns mean. You see them all the time. And then we go to numeric patterns. So remember, there's always that connection in geometry between the visual and the mathematical, but numeric patterns are changing numbers by a plus, a minus, a multiplication, or a division. Means like, they'll lay out a string of numbers like this, and then you got to think about, okay, how are they going from 1 to 4, 4 to 9, 9 to 16? What would you say, Mr. Scritchfield?
Well, this actually has a double pattern inside of it, but those numbers, and again, this is some familiarity. We can all recognize arrows and which way they're pointing and so on, and you're familiar with that. So the same thing here, it's just familiarity with these numbers. Those are all perfect squares, and so that, just because I've seen that so many times, that rings out to me.
Yep.
But it may not to you, I don't know. But 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, and that's the pattern that's developing there.
And then the second pattern, if you missed it, Mr. Scritchfield said there's really two there. One, if you look at it, from 1 to 4, it's a difference of 3, and then 4 to 9, it's a difference of 5. 9 to 16, it's a difference of 7.
So we're adding the odd numbers.
Yeah, we're
as we
adding
go.
on odd numbers in the sequence each time. So that you could look at it two ways. You're going to get to the same place. So the next one will be 25, which would be adding 9 to 16, or it's just 5 squared. And then the next one's got to be 36, which is 6 squared, or just adding 11
Right.
to 25. So I mean, there's patterns there, and we did different things. We did squaring, or we did adding odds. So
Right.
it's you can find different ways to get there, and that's an important thing to remember too.
Yeah, yeah. So different kinds of patterns that we're looking at.
Yep.
We get to a branch of geometry here that really we split geometry in two parts. We have what's called inductive reasoning, and we have what's called deductive reasoning. And most of geometry is deductive reasoning. Most of it's very logic-based, step by step. If this is true, then this has to be true. If that's true, then this has to be true. But we do look at inductive just a little bit, and inductive has to do with what we were just saying, patterns.
Yep. Patterns.
You see this pattern developing over, so you just have to assume that that pattern is going to continue.
Yep.
And happen again. And so it's based on observation is inductive reasoning. And so you observe a pattern going on. Okay? So inductive reasoning is looking for patterns and then making a conjecture, it's called, or making a hypothesis of something that's going to continue happening based on that pattern. So you're assuming that something's going to continue on once you've seen the pattern happen for a while.
Mr. Scritchfield, have you ever paid attention to my inductive pattern that I have every Friday, how I dress?
I have not.
You have not?
No.
Have any of you kids picked it up yet? Pay attention the next couple Fridays and see if you can figure out what my inductive pattern is for how I dress every Friday.
But does that mean you have to dress that way every Friday?
Yes.
Okay.
I've been keeping it going for 9 years now.
Okay. So based on the pattern, that will continue, I guess. We'll just have to look out for Mr. Bedell on Fridays.
And notice that the key question that Mr. Scritchfield asked me was, because I said it was an inductive pattern, he said, does that mean you always have to follow that? And I said, yes. And that's kind of the key for inductive reasoning is going to be this next bullet, I think, that comes up about conjectures. Oh, no, maybe it's on the next slide. But in order to be an inductive reasoning, it has to always take place.
Right.
It has to be a consistent pattern that never changes.
For that reasoning to be true.
Right.
Right. So that term conjecture, is defined here, an unproven statement based on observations or a pattern. So again, we're observing a pattern, we're assuming that that's going to continue, and so we can make a conjecture that that's going to happen. And so here's a conjecture, all girls do go to the bathroom in groups, don't they?
Yep.
Yeah, always happens. So the girls don't say that that doesn't happen, we know it does, so. All right, so that's inductive reasoning.
What are you guys talking about in there?
I don't know. I don't know. You wouldn't think they'd hold hands or anything, but I don't know what they're doing in there.
Inductive reasoning. So we're looking still at inductive reasoning, but to be true, and this kind of goes back to what I was discussing with this scripture a few minutes ago, a conjecture must be true in all cases.
Right.
And so down that, if you go back to that previous one, then is that all girls go to the bathroom a true conjecture then, Mr. Scritchfield?
I don't know. I would think not, because obviously some girls go to the bathroom by themselves. But,
Right.
Yeah.
But anyways, I mean,
but that's a conjecture.
Yeah, it is
And so
a
you would
conjecture.
have to have an instance to prove that wrong.
Right.
If it's not true inductive reasoning.
right. And so just remember, guys, and conjecture has to be true all the time. So, I've really made it a habit because I use it every year to have the same pattern every Friday, how I dress. See if you can catch on to it. It's really not that hard.
So that's what we're going to talk about here.
Yeah.
What if we did catch a girl going to the bathroom by herself?
Yeah. Or I didn't do what I said I'd do on Friday.
Or if you dress differently somehow on a Friday? What
That's
would
right.
that be? One Friday.
One Friday.
Just one Friday is all it would take.
One Friday would all it would take, and you guys could call my bluff. And to be false, it would be called a counterexample. Now, you've seen this in algebra. We talk about counterexample in algebra. But to be false, only one counterexample is needed. And a counterexample, guys, is a specific case where the conjecture is false. And so if you can prove it wrong, as Mr. Scritchfield just said, one time,
Yep.
then you disprove the whole thing. Okay? You've just fixed the whole idea or broken the whole pattern by that one counterexample.
Right, right. So if the statement happened to be that all angles have to be less than 90 degrees, all you have to do is show an obtuse angle, and that's a counterexample.
Yep.
And so we'll have lots of cases like that really throughout the year.
Yeah.
We use counterexample throughout the year. You'll hear that term several times.
Yep.
Really, that's probably the main thing out of this section is counterexample.
Right. And it's an important word. I mean, we talk about it a lot, and you use it throughout all your years of math.
Right.
So,
It just disproves a statement.
yeah.
All right. That's all there is in this section. It's a pretty quick section. We're going to look at some patterns and so on in our assignment and go from there.
Yep. Okay.
We'll see you guys in class.
Pay attention to that pattern. See if you can
That's
catch
right.
on.
Look at Mr. Bedell on Fridays from now on.